Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss the displacement and acceleration measurement. Regarding displacement measurement, we will discuss first we will discuss on LVDTs, then capacitive transducers, how capacitive transducers can be used for the measurement purpose. And for acceleration measurement, there are accelerometers which are piezoelectric type and seismic type. So both type of accelerometers we will be discussing here. To begin with, with LVDT, it is a very popular displacement measuring device. This is linear. So LVDT is linear, variable, differential, transformer. And as like other transformers, this also works on the principle of mutual inductance. Mutual inductance means there is a flux change in primary coil, there is going to be the induced EMF in secondary coil, and which depends upon the mutual inductance between these two coils. But in LVDT, there is one primary coil and there are two secondary coils. There is one primary coil and there are two secondary coils. The reason I will explain to you later. Now, in this, between these two coils, we simply put an iron bar or an iron rod. So, the flux interaction between these two coils can be increased. So, the moment this core, it is called core, right? So, when the core moves in either direction, right, there is a flux interaction between this coil 1, 2 and 1 and 3, and due to this induced EMF is produced, right? And if we are able to measure this induced EMF, and if we can relate this with the displacement in this core, then this transformer can very well work for as a displacement measuring device. The property of LVDT is it can measure wide displacement with 0.5% linearity. That is why it is very popular. Now, regarding the working principle, if we start with, suppose there is an excitation voltage. So, it has to have AC excitation voltage with an RMS value ranging between 3 to 15 volts. This order of excitation is given to the primary coil, and which induces secondary coil ES1. Let us say this is ES1 and this is ES2, right? So, it is something like this: excitation voltage, and this is time. So, excitation voltage is like this. It is an AC, alternating current. There is a core. If core is in the middle, then it is balanced, right? And in both the coils will get the waveform as like this. In both the coils, but this is phase lag, right? Now, if I reverse the polarity, I mean if I connect this one 2 to 4, if I connect this 2 to 4 and take out this and measure voltage here, right? That is why we take two coils. Now, it will be clear to you, when the core is in the middle, in the neutral position, there is going to be no output, because the output in the second coil has reversed, right? So, it will be something like this. Reverse of this. So the output will be cancelling out from ES1 and ES2 and you'll be getting no deflection in the LVDT. But the moment we move in the either direction, the deflection will start and the variation of this output, ES, is linear with the displacement in the core. And finally, we are going to get, if we superimpose these two waveforms, and this is the linear part. This is the linear part where we will be operating, the LVDT will be operating, right? Because here the variation of voltage with distance is linear. Now, let us do some analytical work on this LVDTs. So first of all, we will apply the Kirchhoff's law for voltage loop. So for here, for primary, it is going to be current in primary, current in primary coil, right, multiplied by the resistance of primary coil plus self-inductance of primary coil and primary coil divided by dt minus excitation is equal to 0, right. Now here excitation voltage we can take to the right hand side. Now in the secondary side, ES1 is equal to M1 dIP IP by dt. ES2 is equal to M2 dIP by dt. So difference of these two, this is differential, that is why it is called differential. Now difference of ES1 and ES2 is coming here, so it is going to be ES is equal to ES1 minus ES2 is going to be M1 minus M2 dIP by dt. Now let's go back to this equation. Now IP RP can always be written 1 by D IP RP plus LP dIP is equal to EX. Okay, and from here we can get dIP as 1 by D 1 by RP plus LP EX. Just dIP from here and dIP from here can be taken out, and once we take the dIP and dIP out, this is LP, right? So we are going to get this expression. If we want to further simplify this, then we will get, now this dIP we can put here. If you are putting dIP here, then output we are getting as, so output is M1 minus M2 D by dLP plus RP EX. Now from here, if we divide this by RP, so we will be getting this by RP, this is also RP, and here it will be one. Now L by RP can be taken as lambda, time constant, and we can all comfortably use first order equation, solution for the first order equation, and that is going to be equal to EO by, this is excitation voltage, EX, D is equal to M1 minus M2 D, by lambda D plus 1, where we are already lambda, I have explained, lambda is equal to LP by RP. Now LVDT can also be used. Suppose the frequency of input is 20 hertz, or LVDT can go for a high frequency input also, because in potentiometer there is the limitation, it cannot go for more than 50 hertz. But LVDT we can go for higher input, and in that case EO by excitation J omega or I omega, now this is D by RP, okay, then it is equal to omega M1 minus M2 divided by RP divided by omega lambda whole square plus 1. Right? And rest of the analysis we can do as we did in the case of first order systems. Now, LVDTs have variety of applications, right? And the best part of the LVDT is it can accommodate very high order of displacement if you compare with the potentiometer. And linearity is another benefit of using LVDTs. And linearity is another benefit of using LVDTs. So after LVDTs, we'll go for the capacitive transducers. Now in capacitive transducers, it works on the principle that if there are two plates which are charged with positive and negative charge, right, then capacitance is equal to epsilon A by D, where epsilon is permittivity, and if permittivity is equal to relative permittivity multiplied by absolute permittivity. D is the distance between these two capacitors, and A is the cross-section area. So the moment this plate is moved in either direction, this direction or this direction, there is going to be change in C, right? And if you are able to measure the change in C, or we can relate this C with this movement, we can find the displacement. Now instead of using one, if we use bank of capacitors, or let us say two capacitors, if two capacitors are used and they are put in series, so plus, minus, right? And they are put certain voltage under voltage E. E is applied between these two, right? And this capacitor has capacity C1 and this has C2, right? So total capacity of the capacitors is going to be, because they are in series, 1 by C1 plus 1 by C2, or C is equal to C1 C2 by C1 plus C2. And charge on the plate is going to be Q is equal to CV is equal to C1 C2, C1 plus C2 and E. Now here there is a displacement initially, okay, there is a displacement in the middle plate, and displacement in the middle plate is, let us say it is X. Just a minute, it's T X. Displacement, sorry, this is plus minus. Now displacement of middle plate is X. This middle plate displacement is X. Now there is a displacement in the this plate of X, and voltage is Q is equal to CV, right? If you want to have voltage V, then we can take Q by C, right? And then this Q is nothing but C1 C2 by C1 plus C2 into E, and this voltage Q is divided by C, so it is divided by C1. So voltage is going to be C2 by C1 plus C2 multiplied by E, right? And similarly, we can find the voltage for the second capacitor. This is V1. Similarly, we can find the V2 as C1 plus C2 into E, right? When we are talking, if we are using this formula, C is equal to epsilon naught D by, sorry, epsilon naught A. A is constant. Epsilon is same for every capacitor. A is same. Only it is going to be C1 is D, sorry, T plus X, and C2 is equal to epsilon A T minus X. Now putting these values here, we'll get the final expression as, and we'll take the difference of V1 and V2. Then final expression for V1 minus V2 is going to be X by T. So simply we can take V is a function of X because T is constant. So that is how we can use these capacitive transducers for distance measurement. And the properties, the main property of these transducers is they can sense very small displacement. They can sense there's a displacement of the order of, let us say, 2.5 microns, 2.5 micrometer, or 0.0025 millimeter. They're easy to fabricate, they are not very costly, and output linearity is also good. In these transducers also, they don't have wide range, but the output linearity is good for these transducers, and they can also measure static and dynamic input as well. So they are good for both, for static and dynamic input as well. So after this displacement measurement, we'll go for the acceleration measurement. Acceleration measurement techniques. Now, acceleration measurement, we can go for the piezoelectric type of accelerometer, where piezoelectric sensor is used for acceleration measurement. So in the base, this is a substrate where the this has to acceleration has to be measured, and there is a housing. Right, and in this housing, piezoelectric transducers is fixed, right? And above the piezoelectric transducer, there is mass M, and this is transducer. And this transducer, and we have connections to this transducer, so we can always have output of this transducer. Now we know that force F is equal to ma. Mass is constant here. Mass is not varying. So force is proportional to acceleration. It means force exerted on this transducer is proportional to the acceleration. Now acceleration is always expressed in terms of g. Acceleration due to gravitation. So output will be expressed in terms of, let us say, millivolts per g. Okay, because acceleration is always, because this is standard acceleration. So when the entire system is moving up, when it is moving up, the force on this transducer will increase, and when it is coming down, then this force on this transducer will reduce, right? Because acceleration due to gravity will change when it is moving, either moving up or it is either moving down with certain acceleration. Accordingly, we will get the output from the transducer, and that is how we can make, or we can find output of the transducer is a function of acceleration in the body, and this is how the acceleration is made, is measured with the help of piezoelectric transducers. And first of all, they are not very expensive. Why we use piezoelectric transducers? Because they are not very expensive. They have output impedance is high. Okay, frequency response, we can go up to 10 to 15 hertz for frequency response. Sensitivity is approximately 10 to 100 millivolts per G, right? This is the sensitivity of this is the range of the sensitivity of these transducers. But these transducers are temperature sensitive. I mean, if there is a change in the temperature, the output will be affected. So temperature has always interfering effect in the case of these type of accelerometer. And these accelerators are also subjected to hysteresis error. So there are two drawbacks of these type of transducers. Now, in these transducers, we use the piezoelectric crystal, which has natural frequency higher than 100 kilohertz. So natural frequency of the piezoelectric crystal has to be higher than 100 kilohertz, right? And the benefit of these type of accelerometer is they are very light in weight, because primary sensing element has, maybe 5 grams or 10 grams. So they are very light in weight. That goes in the favor of these type of transducers. Now, another type of acceleration measuring transducer is seismic type. Now, seismic type of acceleration measuring devices. So, in seismic type of system, again there is a substrate, and on the substrate this transducer is fixed for measurement of the acceleration. It has a seismic mass m. It has seismic mass m balanced on a spring and a dashboard. So there is a mass hanging in this accelerometer on a spring with some constant k and a dashboard, right? And for the measurement of displacement, there is a arrangement for the measurement of displacement x. And now if this substrate is under vibrations. So vibrations are, let us say, x1 is equal to xo cos omega t. So this will also vibrate, and this vibration will have certain amplitude, right? So we can transform this arrangement like this. There is a spring k fixed to mass m. Mass m, there is a dashboard, and this is x2t, this is let us say this is x2, and this is x1 is equal to xo cos omega t. Now we can do this vibrations analysis. So we'll start with the basic equation. The basic equation is, I'll rub it off. So the basic equation is m d square x by dt square plus c dx2 by dt plus k x2. This is generalized equation for the vibration having a spring and a damper, is equal to, here c dx1 by dt plus k x1, right? So this is input. This is input, and this is output. Now here we can further modify this equation as d square x by dt square, this is dt square, plus c by m dx2 by dt plus k by m x2 is equal to c by m dx1 by dt plus k by m x1, right? Now, after this, if we want to have solution for this, then x1 can be put as x1 is equal to xo cos omega 1 t. Now, the moment we put this x1 is equal to xo cos omega t, now this equation becomes xo, now this will be copied here, the same, it will remain same, is equal to xo k by m cos omega 1 t minus c by m omega 1 sin omega 1 t. Now, because x is equal to xo cos omega t, omega 1 t. So, we are just differentiating it once, and then k by s cos omega t, right? Now, solution for this, now if you want to have solution for this, that is x2 minus x1 are going to be e raised to power c by 2mt a cos omega t plus b sin omega t plus m xo omega 1 square cos omega 1 t minus phi divided by k minus m omega 1 square whole square plus c square omega 1 square raised to power 1 by 2. And this is out of this solution, we will deal it as a second order equation. Out of this solution, this is a transient phenomena. So, it will die out after some time. So, if this is vibrating, I mean the substrate is vibrating, this is going to be the response, final response. Because this is a transient phenomena, with time it will die out, right? So, we can find from here omega is equal to k by mo minus c by 2m whole square 1 by 2 when for c by cc is less than this, c by cc is less than 1 for underdamped type of system. Now, after this, if we want to have steady state harmonics, they are going to be x2 minus x1 o is equal to xo omega 1 by omega n whole square divided by 1 minus omega 1 by omega n square plus 2 c by cc omega 1 by omega n square and total raised to power 1 by 2. Okay. Now, if we draw a curve for this, now if you draw a curve for on abscissa, we can take omega 1 by omega n. On ordinate, we will take x2 minus x1 omega n square divided by AO. Now, how we are taking AO is the amplitude of input. Where A is the amplitude, x2 minus x1 omega n. How we are getting this? We are getting this when we just take this x2 minus x1 O divided by xo omega 1 square divided by omega n square. Now, xo omega 1 square is AO, omega 1 square by omega n square, right. So, this xo omega 1 square is AO. So, between these two, x2 minus x1 omega n square by AO and omega 1 by omega n. This is omega 1 by omega n. right? So this is omega 1 by omega n. And if we draw a curve for this, for different value of C by Cc, so when C by Cc is 1, the curve is like this. And omega by omega n, I'll give you the values. This is 0.5, 1, 1.5, and 2. So this is C by Cc 1. When we take C by Cc let us say 0.4, it is going to be like this. And definitely if it is 0.1, the curve is going to be like this, right? Now from here, we have to find the relation between displacement and the acceleration of the body. Now for this purpose, regarding, yes, there is going to be phase angle also, and the phase angle is going to be, in this case, phi is equal to tan inverse CW1 divided by K minus M. Okay, this is not for this one. Now phase angle here is going to be phi is equal to tan inverse 2C by Cc omega 1 by omega n divided by 1 minus omega 1 by omega n whole square, because it's a cyclic input. So for cyclic input, this is going to be the phase angle, right? I will take one numerical, then it will make clear how the acceleration is measured with the help of these type of instruments. There is a seismic instrument to be used for the measurement of linear acceleration. It has omega n, natural frequency 100 hertz, radians per second. So there is a small seismic instrument used for measuring the acceleration, and omega n is equal to 100 cycles per second. Oh, sorry, radians per second, not cycles per second. Radians per second. Fine. And a displacement sensing transducer which detects a maximum of plus minus 2 mm. So maximum detection of displacement transducer is plus minus 2.5 mm. Okay. The certainty in displacement measurement is uncertain. It is uncertainty in the displacement measurement is plus minus 0.025 mm. This is the uncertainty in the measurement. Calculate the maximum acceleration that may be measured with this instrument and the uncertainty in measurement, assuming omega n is known exactly. So we know the natural frequency, it is exact, 100 radians per second. There is no error in this. Now, for this is the maximum measurement which can be measured with the LVDT. Now let us look back the expression for acceleration parameter, that is x2 minus x1 O omega n square divided by AO, right? When AO is maximum, W1 by Wn is tending to 0. So if you look at this graph where we took this, let us say this is Z parameter. So Z parameter and omega by omega n. So omega by n, when omega by omega n was 1, then Z parameter was the highest. And then it came down, this is 2, let us say, omega by 1 or 2. And this is value 1. So when omega 1 by omega n tending to 0, and this is tending to 1, or this is equal to 1. So AO can be written as omega n square x2 minus x1 O. So it is 100 square divided by 2.5 divided by 1000, and we are going to get 2.5 meter per second square. So uncertainty in the measurement of A is equal to del A by del X, uncertainty in the measurement of X whole square raised to power 1 by 2. So del A by del X is omega n square, that is 100 square, and uncertainty in the measurement of X is 0.025. And then we take, whole square, and then it is half. So out of this, if we solve this, we will be getting 0.25 meter per second square as the uncertainty in the measurement of acceleration. That is all for today. Thank you very much.